lecture, we are going to review Chapter 4, Atmospheric Moisture. So first, let's look into the Northern Hemisphere and the Southern Hemisphere. So here, like it states on the slides, the Northern Hemisphere is known as the land hemisphere because most land is concentrated in the Northern Hemisphere compared to the Southern Hemisphere, which it's mostly water or the ocean basins, and this is known as the Oceanic Hemisphere. And we can see that here with the map of the world's oceans, and again, the equator separates the Northern Hemisphere with the Southern Hemisphere, so that is why they have that name attached to both of them, so the Oceanic Hemisphere and the Land Hemisphere. I also want to touch on the hydrologic cycle. So when we're looking at the hydrologic cycle, we're looking at the changes of the phase changes of water and how it cycles through the atmosphere, on land, back to the ocean. And here it states, though the concentration of water vapor in the atmosphere is low at 0.03%, it is very important. So water vapor transforms into cloud particles through the process of condensation, like we see here. And the clouds, they are composed of water droplets and ice crystals. And when these water droplets and ice crystals grow very large, they will get heavy, and due to gravity, they will fall onto the Earth's surface as precipitation or rain. And here we see another important term called sublimation. And sublimation, it's the transition of a substance directly from the solid to the gas state without passing through the liquid state. And also we see another important term called infiltration, which we see here, and this is a portion of the water that falls on land and soaks into the ground to become groundwater. And the remainder, which flows along its surface, is called runoff or overland flow, like we see these terms. So again, the hydrologic cycle, it's the continuous movement of water from the oceans to the atmosphere, from the atmosphere to the land, and back, and from the land back to the sea. So the precipitation that falls into the ocean has ended its cycle and is ready to begin another cycle. And another important term we see here involved with the hydrologic cycle, it's transpiration. And transpiration is when water evaporates from plants, especially from their leaves. So it's like the plants are sweating, and this process is a key part of the water cycle on Earth. The amount of water a plant loses depends on many things. These include the plant size, how much sunlight it gets, the temperature, how humid the air is, how fast the wind blows, and how much water is in the soil. So transpiration also helps plants control their temperature, keeping them cool. So water is a unique substance here on Earth. Water is the only liquid on the surface of the Earth in large quantities. Water exists in all forms on Earth, meaning it exists in its liquid state, solid state, and gas state. And we're going to learn in the diagrams later in lecture that ice is less dense than liquid water due to the crystalline structure of the hydrogen bonds. And we'll look at that in the next slide. And water has a high heat capacity. We covered the term high heat capacity in last week's lecture, and high heat capacity means that changing its temperature requires considerable amount of energy. So water requires a significant amount of heat to raise its temperature by 1 degree. And also water has a unique ability to form hydrogen bonds. And all these properties influence Earth's weather and climate, which is favorable to life as we know it. So here let's look at figure 4.2, which is called hydrogen bonding in water. And let's look at diagram A. So with diagram A, we have a water molecule, which consists of one oxygen atom, here in red, and two hydrogen atoms. So because oppositely charged particles attract, a hydrogen atom on one water molecule is attracted to an oxygen atom on another water molecule, which we'll see here in diagram B. So water molecules are joined together by hydrogen bonds that loosely bond a hydrogen atom on one water molecule. So we have the hydrogen atom here, and then it will connect with an oxygen atom on another water molecule like we see here. So this is the process of hydrogen bonding. And diagram C, we see the water's solid phase has a crystalline structure. And if we notice here with the water's solid phase, there's a lot of empty spaces, which makes it less dense than the liquid state, which we'll see in the next diagram. So we've covered the concept of temperature, and as we know, the higher the temperature, the faster the motion of molecules. In this case, water molecules, they'll move very, very fast. If you heat up, if they get heated, so you can think of it when you're boiling water in a pot. Again, the water is vibrating, water molecules will be vibrating really, really fast, and they're bouncing off each other's nuclei. Whereas lower temperatures, the molecules slow down, they move very slowly and arrange themselves into hexagons, which we see with the crystalline structure, and then we'll see in the next diagram as well. And it takes billions of water molecules to produce one tiny liquid water droplet. So this diagram here is showing us the phase changes of water and the calories, whether it's absorbed or released. And calories is the heat involved when water changes state, and it's measured in units. So 1 calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius, or 1.8 degrees Fahrenheit. So as we look at this diagram, it's stating here when water changes state, hydrogen bonds either form or are broken. And here, through the phase changes of melting to evaporation, the hydrogen bonds are being broken down. And here, in its gas state, the hydrogen bonds are completely broken and the water vapor molecules are moving freely around. So again, like it states here in the diagram, water molecules and ice are bonded together in a configuration that has lots of empty spaces, like I pointed out in the previous slide, which accounts for ice being less dense than water. And here, when solid ice melts into liquid water, some of the bonds are broken and the water molecules become more closely packed, making it more dense than solid ice. And then we have the process of evaporation. So when liquid water evaporates, all of the hydrogen bonds are broken and the water vapor molecules move about freely. So these are the phases where hydrogen bonds are being broken down. And then we could see here with the process of from the gas to liquid, which is the phase change known as condensation, and then liquid to solid ice, which is the process of freezing the liquid to become solid. This is forming the hydrogen bonds. As well as deposition, you're forming the hydrogen bonds. And also take note of the calories released here. So for condensation, about 600 calories are released. And it's important to note that through these phase changes, latent heat or hidden heat is either released to the environment or taken from the environment. So, for example, when water vapor condenses into liquid water, it is releasing the heat that was stored in the water vapor molecule. And as it's releasing the heat to the environment or to the atmosphere, this process is what fuels storm systems. And here, with the phase changes of melting and evaporation, the heat is taken from the environment, and as the heat is taken from the environment, it is a cooling process. And for example, you feel this process when you're getting out of the pool. So the liquid water droplets on your skin will evaporate, and then you feel a cooling sensation. So again, just know melting and evaporation is a cooling process, and condensation and freezing is a warming process. So again, when we're looking at evaporation and condensation, we're looking at the processes. So another important term is saturation, and saturation, the definition is when the number of molecules escaping is balanced by the number of molecules returning. So we'll see examples of the balance of water molecules evaporating, which would be escaping, and the balance between condensation. So with the same number of vapor molecules in the air, cool air saturates faster than warm air. And warm air can hold more water vapor molecules before becoming saturated than cool air. So we'll take a look at those diagrams later in lecture. And like I mentioned before, latent heat is hidden heat, and here it states that adding heat to melt ice does not result in a temperature change. So, for example, when the ice in a glass of water melts, the temperature of the mixture remains at a constant 32 degrees Fahrenheit until all the ice has melted in your cup of iced water. So, again, if the added energy does not raise the temperature of ice water, where does this energy go? In this case, the added energy breaks the hydrogen bonds that once bound the water molecules into a crystalline structure. And here we're looking at, for melting 1 gram of ice, this requires 80 calories, and freezing 1 gram of water releases 80 calories. So latent heat is also involved in evaporation, the process of converting a liquid to a gas. And again, evaporation is a cooling process. And then condensation is a warming process. Sublimation is a process that turns a solid to a gas, and then examples of that are disappearing of ice cubes in the freezer, which is a result of sublimation, and then deposition is the reverse process of changing a vapor to a solid. And here we have frost accumulating in a freezer, which is a result of deposition. These are examples of condensation and deposition. So condensation of water vapor generates phenomena such as dew, clouds, and fog. And frost on a window pane is an example of deposition.